Assume we are taking a tour of the metallurgy industry.
Hmm?
Assume we are taking a tour of the metallurgy industry.
Yeah.
Okay,
Let's
I'll
see.
assume.
Okay, let's start with this now. Um, Metallurgy mainly deals with how to extract metal in simple terms. Okay,
Oh, okay.
and mainly, if you notice this one, abundance of elements in the earth crust. You know, basic literature. What you need to know is that oxygen is the most, then silicon, aluminum, and iron.
Okay.
Okay,
Yes, sir.
right. There are non-metals, metals, transition metals, all of them in different forms can be found in earth crust. And the way they are found is what we call them as minerals. Okay.
Hmm.
If they are generally insoluble and less dense, they are deposited mostly on the earth crust. Okay.
Okay.
And when it comes to metallurgy, it is mineral. It is mostly a naturally occurring substance in which metal exists in a free form or in a combined form. Okay, they are
Free
generally
form or combined
insoluble.
form.
And they are generally insoluble.
Okay. Yes, sir.
Usually a nitrate mineral does not exist because all nitrates in generally are water soluble. Okay,
Okay.
now if these minerals are useful and we can make an economic viability out of it, then that metallurgical extraction, I mean that metal form is called as ore. Okay, mineral and
Okay.
ore are one and the same, except that ore is only used when it is economically feasible. Okay,
So, okay, fine, got it. Hmm.
right. So it is like this. Ore is like a subset of mineral.
Mineral. Hmm.
Okay. So this also makes sense that all ores are minerals, but all minerals are not ores.
Yes, sir.
If there are certain impurities present along with this ore, those are called as matrix or gang particles. Okay.
Hmm.
And different group elements will form different type of ores. Generally, most of group 16, right?
Yes, sir.
Group 16 elements that includes oxygen, sulfur, selenium. These
Yes.
are the major forms that you will notice, right? So most of the sulfides and oxides are water insoluble
For
and
O's.
they are found as ores. Okay.
Okay. Yeah.
And this comes with the great polarizability of S2 minus, as compared to that of O2 minus. Sulfur is bigger in size, it will have more polarizability. And it also comes with the fact that P and D block elements usually, as it becomes more higher and higher, and it becomes more
Hmm.
d electrons present in it, their polarizing power is more. So
Correct. Yeah.
polarizing power is more covalent character.
Right.
Polarizability is more covalent character. That's why oxides and sulfides generally show high covalent character, and thus they are insoluble and exist as more ores. Hmm?
Right.
Next, see these examples. PBS. PBS is called galena. The ore's name is galena. CuFeS2, copper pyrites. Ag2S, argentite. AgS, cinnabar. Okay, and
Hmm.
all these were sulfide ores, correct? And if you have
Right.
O2 minus, they are generally with lower or lighter metals like aluminum, calcium, okay, like this, or iron, Fe2O3. Got it?
Got
Hematite,
it.
limestone, bauxite, these are the ones. Other than that, we can also have carbonates in the form of dolomite, or we can have D block elements like pyrolusite and chromite. Hmm?
ये सब नाम याद रखने.
There is a list which I'll show you. पूरे list याद रखना है, रटना पड़ेगा उसको. Okay.
Okay.
Now, when it comes to ores, there are two forms: native ores or combined ores. Native ores means they are found in their free form, like gold, platinum, silver, mercury, and so on. Combined form, except for gold and platinum, most of the metals will be found in combined form. Okay. Within combined form, we can have halide ores, oxide ores, or sulfurized ores. Within
Hmm.
oxide ores, we can have basic oxides, or we can have nitrates, sulfates, phosphates, carbonates, and silicates. Okay.
Okay.
More
Yes,
than
sir.
nitrates, it is nitrites. Okay, because nitrates are anyway soluble. So nitrites, sulfates, phosphates, carbonates, and silicates. Hmm.
Yes, sir.
This is the list of ores which you need to know. The one which I marked are more, those are more important ones. Okay,
Okay. Hmm.
got it. So as of now, I'm not going about it. This is first to learn. This is the revision sheet. Okay, so to rewrite
Okay.
that. Clear? Hmm.
Okay.
Now, next. The process of the metal extraction is called as metallurgy, and extractive metallurgy is a separate branch of science which deals with extraction of metals from ores.
Okay.
Now, usual method, an engineering method, is what you get ores from mines, then we pulverize them or crush them or grind them, okay?
Hmm.
Convert into a powdered form. And in a powdered or a coarse form, once you get that, you will do something called dressing of ore. Dressing of ore means you're trying to separate impurities from the main composition of metal ore. Okay. And the part which you will get where you will have more concentration of metal ore, that is called concentrated ore. Hmm.
Okay. Hmm.
So this procedure from the powder ore to the concentrated ore, this is called as dressing or concentration of ore. Okay.
Hmm.
Next, from the concentrated ore, you will convert into a crude metal, okay, and impure form of metal, and this can be done by reduction methods. So there are various reduction methods. So you can follow as per the economical viability. One reduction method is followed, and
Right.
from the crude metal, we will be further refining to convert into pure form of metal. Okay, this is
Right.
a typical flow chart of extracting metals. Now,
Yeah.
out of this, the first part being the concentration of ore. See, crushing doesn't have anything great to offer other than just crushing it and converting into powdered form. Okay, it is more of a physical activity there. So we
Ah,
need to
okay.
convert everything into powdered form. Later on, the concentration or dressing or beneficiation of ore. This is about removing out the visible impurities from the ore. Now, this can be done
ठीक
in
है.
two ways. One by physical separation processes or chemical separation processes. Okay.
Okay.
In physical separation processes, these three are the main ones: gravity separation, magnetic separation, and froth flotation. Hmm. Super.
Hmm.
Now, as you keep reading, right, you keep doing these questions as well. Okay. It makes it easier whether you have followed it or not. Okay. Hmm.
Okay.
Check out. In physical separation, gravity separation, which is also known as leviation, it is a
Okay.
method to remove the lighter and small impurities with the help of a particular type of equipment. Okay. First one
Hmm.
being hydraulic wash. So you can see first one being hydraulic wash. Okay.
Hmm.
When the ore is heavy compared to the impurities, then the ore is concentrated by gravity separation, which is based on difference in densities. Imagine the powdered form of ore, you are pushing it here. Okay. And from here, you have hot steam which is coming here. Correct.
Right.
So as the stream keeps hitting this, okay, in case if you have an material which is lighter, so that might mix with it and come out here, which will be collected as impurities. And the ores which are heavier, they will fall down anyways. Correct. So they will have the
Hmm.
influence of gravity more. So that will form a metallic ore here. Yeah?
Yes, sir.
So when a powdered ore is mixed in running water, heavy ore particles settle down while the impurity is flushed out. Okay.
Okay.
Now this process can be done by Wilfray table. Wilfrey table, as in you will have a slanted table here with this kind of compartments here. So as the ore along with water keeps flowing, hmm,
Hmm.
now if lighter particles are there, they'll keep on washing away from the surface, and the heavier particles will stay at these corner junctions, isn't it?
Yes, sir.
And these heavier particles which will stay, they are typically ore forms. Okay, clear?
This was gravity.
Right. Okay,
Okay. Hmm.
right. Just a second. So this way you will have, water, running water, and ore being added, and these are all the tables you can see here. Correct.
Yes, sir.
So metallic ores will stay back. The other one being magnetic separation. In magnetic separation, what we will have a conveyor belt here like this. Okay, but that
Hmm.
belt is made up of magnet, so at least it will have a magnetic property on it. Clear? So
Right.
because of that magnetic property, when the ore is being added, powdered ore is being added, and it will start moving around like this. Correct? The
Hmm.
ore will go, and anything which has an impurity will fall little away. Okay, and if it has a magnetic property, that means it will attract to this magnet, it will come up to this point and then fall here. Got it?
Hmm.
So magnetic material will fall very close to the conveyor belt. Non-magnetic will have a motion, like more like a projectile motion, and then fall slightly far away. Okay, so
Hmm.
this way you can separate a non-magnetic material and magnetic material. Okay,
Right.
yeah. Next, if you notice the magnetic material here, that includes Fe2O3, MnO2, FeCr2O4. These are all magnetic material. Non-magnetic as in silica or any other impurity. Got it?
Hmm.
While extracting tin, right? This could be both ways.
Right.
It might happen that tin is actually non-metallic, okay? But along with tin, you will have this wolframite impurity, which is FeWO4 or MnWO4, okay?
Right.
This is iron wolframite or manganese wolframite. This is
Hmm.
magnetic in nature. So the impurity is actually coming here, the desired ore metal is coming here. Understood? In
Hmm.
non-magnetic form. So you can use it in either ways. Got it? It is not
Right.
necessary always that the non-magnetic section only has to have impurity. Okay.
Right.
Next. Next is about froth flotation. Froth flotation is used specifically for sulfide ores. Okay. Sulfides usually form only with heavy metals, which has high polarizing power. Okay. Now here, what we notice first thing, suppose if you talk about adsorption, for example, in Haber process, iron is used as a catalyst so that hydrogen gas does not, make a synergic bonding with the metal surface, which will help in making a better adsorption, and that way nitrogen gas can connect with hydrogen more easily. Correct?
Hmm.
So similar type of adsorption property what we need to check. Okay. Second, another property we need to check is like dissolves like. That means if you have a polar solvent, it usually favors a polar substance to get dissolved. And similarly, now non-polar will help a non-polar substance. Third important, and this is the basic principle behind the froth flotation, is that to convert a sulfide ore into a non-polar by adding a xanthate, because xanthate will have two parts of polar and non-polar parts. Okay. Now, what
Hmm.
does this exactly mean? This particular compound is called sodium xanthate. Okay,
Right.
sodium ethyl xanthate. Clear? Now,
Right.
sodium ethyl xanthate here will have two parts. One part is this one, where you will have C2H5, you know, O, this entire part here. Now, this part is basically non-polar part. While you have this part here, which is a polar part because it has a negative value on it, negative sign on it, correct?
Right.
So in the solution, basically while separating out what we do, we will have a container in which the bottom layer is aqueous layer. Just above it, there is an oil, correct?
Hmm.
So oil is mostly a non-polar layer and this is a polar layer, correct? So
Right.
basically the xanthate will be like a bridge between these polar and non-polar sections, wherein in the polar section we will have S minus and in the non-polar section we will have this ethoxy group. Okay.
Hmm.
Okay. So aqueous solution will have more attraction towards this S minus, while S2 minus, the solvents which I mean metal sulfides which we are adding, they will have more affinity with the uh, non-polar non-polar part. Okay,
Right.
clear. So this is the importance of xanthate. Okay, now how does the process begin? Ore particles are ionic compound, right? To convert them into non-polar species, and xanthate is used for it. Xanthate has two
Okay.
parts. One is a hydrophilic, which means which will attract water, and the other one is collector, which will collect the particles of sulfide, correct? Which is hydrophobic.
Right.
So here it is like this. So you can notice that this R, which is non-polar part here like this will collect something like a sulfide ore here, correct?
Yes, sir.
And this will go and connect it to the water. Okay. So ore
Yes,
particles are
sir.
wetted with the pine oil. So you add pine oil here, right? Here there is an aqueous layer, and then we have a
Okay.
pine oil. While impurities are wetted by water because they are heavy and settle down in the container here, correct?
तो पाइन ऑयल वाले पार्टिकल्स ऊपर आ जाते हैं.
हाँ, नो नो, पाइन ऑयल में मेटल के नॉन पोलर पार्टिकल्स ऊपर आ जाते हैं,
हाँ मतलब
मेटल
जो भी
सल्फाइड।
पार्टिकल्स गेट वेटेड बाय पाइन ऑयल वो ऊपर आ जाते हैं.
हाँ जी, बाकी जो इम्प्यूरिटीज है विच आर पोलर इन नेचर वो पूरे डिसॉल्व हो जाएंगे वाटर में।
ठीक है, समझ गए.
ठीक है। Now, what we do, we will be adding hot air into a propeller here. ऐसे एक propeller रहेगा. This is a kind of a propeller, okay?
ओके.
And propeller will start, moving around. It will
रोटेटिंग.
make
हाँ.
some RPMs here, okay?
यस सर.
Because of which, what happens? The sulfide particles, the non-polar particles will keep combining with each other and start forming a froth, okay?
ओके.
And that froth will start coming because froth will have less density. They'll start accumulating on the surface,
हम्म.
okay? Now, pine oil is acting in two ways. One, it is acting like a frother. That means it is helping it to make the froth. At the same time, it is also acting like a collector. Collector is means what? Collector of sulfide ores. Okay,
ओके.
got it. And anything which is a heavy particle or anything which is soluble in water, they all will settle down in the aqueous layer. Okay.
हम्म.
Now, to when the froth is coming on the surface, froth is nothing but some kind of bubbles, right? Now,
बढ़िया.
obviously, if those bubbles will keep, popping up. So, if you want that bubbles or froth to remain stable for a longer time, we use cresol and aniline. These are called froth stabilizers. Okay.
राइट.
So, they will decrease the surface tension of water, anything which is coming above, and therefore, it will keep that froth for a longer time. Okay.
हम्म.
Clear? So, this is that agitator which will keep on moving, propeller or the agitator, and from here hot air is being compressed, hot air is being given, right? So that particles can mix here and they can start forming the froth. Okay, so these are the
हम्म.
combinations. We'll have water, pine oil, metallic ore, and sodium xanthate. Hmm.
राइट.
Oil is recovered by froth, Okay, first heating, it is due to break the surface attraction, that is any kind of adsorption happening on the surface, that will break away. Second, using dilute HCl, right? Xanthate is an anion of a weak acids, and they are strong base with a high affinity for H plus, so the ore will be removed easily. Okay.
Hmm.
Next, we also use something called depressants and activators in the froth flotation mixture. What is that depressant and activators? Let me tell you. Suppose, see this case, whenever you are trying to extract galena, PBS, and you're trying to make
Hmm.
it into, you're trying to separate it with other impurities. Along with galena, you'll always see some reasonable amount of zinc sulfide present. Okay. But of course, zinc
Right.
sulfide is also a sulfide ore, so it will behave very similar to PBS, isn't it?
Hmm.
So that will also come into the froth. But
Well,
I don't want
yeah.
zinc to come. I want zinc to settle down. Okay.
Well, I mean,
So,
I don't really think that's up to you.
so if I want that zinc to be in the aqueous layer or just separate away from PBS, then what you
And
do, you will add NaCN. NaCN is called depressant. Okay. So
ठीक
it's a
है.
strong base that will react with zinc, forms a complex. Okay.
Hmm.
And this is a soluble complex. So what will it go? Where will it go? It will go to the aqueous layer. And what is the
Okay.
left part? PBS, which is left part, that will go onto the surface as a froth.
Okay. Hmm.
Eh? And now check out. To recover the zinc, we use copper sulfate as the activator. Okay.
Copper
So
sulfate.
once you remove the PBS, of course, we will not let zinc sulfide also, go away, because that is a good source for extracting zinc again. Okay.
हाँ जी. Hmm.
So to bring back the zinc sulfide this time, क्योंकि PBS को हमने हटा दिया, अभी zinc को लेकर आना है वापस. So we can use copper sulfate. Copper sulfate in the presence of the zinc cyanide complex will convert into a cyanogen gas, and copper will convert into this +1 oxidation state. And zinc
Right.
will connect with Zs2 minus and convert into ZnS.
Okay. Hmm.
Okay. So this way, what do we get? We will get the zinc sulfide back into the solution, and from there again we make the froth of zinc sulfide. Okay.
Right.
Mm. So basically, copper sulfate is called as an activator because it is again trying to activate the depressant complex. Okay.
Hmm.
So that's how the froth flotation helps us removing of the sulfides. Okay.
Hmm.
Clear?
Yes, sir.
Let us see some chemical processes. Now we studied three processes which are physical processes. Now let's focus on chemical processes. First one includes leaching. See, the process of selective dissolution of ore in the concentrated aqueous solution of some chemical is called as leaching agent at the room temperature. Okay. So
Okay.
I'm taking a agent here, leacher or leachant. So that when you react with the ore, if it becomes a soluble form, it will become a soluble form
Okay.
here. Then in this soluble form, we will have the desired metal, and the impurities which are left over will remain insoluble. Got
Okay.
it?
Hmm.
Now, then you apply the filter through the filtrate. Once you get the liquid solution here, you add something called an anti-leaching agent. Anti-leaching
Okay.
agent will again regain back the ore which was originally dissolved and get back into a solid form, insoluble ore form. While here, because
So,
the residue
okay.
which is left will have all impurities. This will be the stage of all impurities here, beta. Okay.
ठीक है.
Dekho. I'll show you the examples also. There are
Okay.
different types of leaching. First one being Bayer's process. Okay.
Okay.
This is specifically designed for extracting aluminium. Okay.
Hmm.
See, the process is used mainly for bauxite. The main ore for aluminium's extraction is bauxite, Al2O3.2H2O. Okay.
Right.
Now, Al2O3.2H2O has mainly two types of bauxites. One is red
Hmm.
bauxite, the other one is white bauxite.
Right.
If you have red bauxite, that means you will have the impurity of Fe2O3. Fe2O3 is the impurity there. If it is white bauxite, that means you'll have SiO2 and TiO2 as the impurity. Okay, main impurity
Okay.
is SiO2, which is white bauxite. Clear?
Hmm.
And see, if you have a mixture of Al2O3 and Fe2O3, react with NaOH. So NaOH will get dissolved. I mean, L2O3 will get dissolved in NaOH. But
Right.
Fe2O3 is already a basic form, NaOH is a basic form. So nothing will happen to Fe2O3.
Okay. Hmm.
Okay, clear? And what do we get
Yes,
here is
sir.
NaAlO2. Okay.
Hmm.
Now this is a soluble form of aluminium, correct? So what we do, that soluble form of aluminium, if you react with carbon dioxide at low temperature, this sodium will
Hmm.
convert into sodium carbonate, which is dissoluble form, and aluminium will take water and convert into aluminium hydroxide. Okay.
Okay.
So this is soluble form, this is an insoluble form.
Right.
Okay, beta. Right. Now what we got, this Al2O3, if at all you simply heat it from here, water will be escaping out. So what do we get? Al2O3. Done. So did we
Yeah,
regain
two,
the
three.
back the original compound or no? Right? Original ore is this one
Hmm.
only, but this time the impurities are being dissolved. Okay,
Okay.
because
Yes, sir.
Fe2O3 हमने हटा दिया इसमें से, है ना?
ठीक है. Hmm.
The other case where we see leaching is MacArthur Forest dynamite process. This is mainly used for extraction of native metals like gold and silver. Okay,
Right.
and it can be done by either directly existing impure gold, impure silver, or Ag2S.
समझ गया. Hmm.
They themselves are ores. Okay,
Yes, sir.
here the leaching agent used is NaCl. NaCl in the presence of O2. So if you have a metal in the presence of O2 with NaCl, then
Hmm.
this metal, silver or gold, will form a soluble cyanide complex.
Okay.
Okay,
Hmm.
and rest of the impurities present, maybe silica or iron or anything, that is remain as insoluble form. Hmm. So you
Okay.
filtrate it. After filtration, you will get this metal cyanide form. Then react with zinc. Okay, clear? On reacting
Okay.
with zinc, this entire metal will convert into, sorry, this entire lithium will convert into Na2ZnCN4 and metal will get reduced. Done.
Right.
In the case of Ag2S, we'll have Ag2S plus NaCl, you will get this one plus S2 minus. And
Right.
Ag2S plus NaCN plus O2 will form NaAgCN twice plus sulfur plus SO4 2 minus.
Yes, sir.
And again, this is something which you can regain back, correct? So if you
Yes,
add
sir.
the zinc to it, so it will replace silver by zinc. Done.
Yes, sir.
Hmm. Next, see, when it comes to extractive metallurgy,
Hmm.
there are various type of metallurgy depending upon the feasibility, economic liability. We need to check. First,
Okay.
we can reduce metals via electrical energy, so we call it as electrometallurgy. Hmm.
Okay.
You can reduce metals by using water, then we call it as hydrometallurgy.
Okay.
We can reduce metals using heat, then it is called pyrometallurgy.
Okay.
Okay. Now, highly reactive metals, which you call it as the electropositive series, includes lithium as the highest reactivity, then potassium, barium, strontium, calcium,
Hmm.
and then sodium and magnesium. Okay.
Right.
This is electrometallurgy.
Right.
Now, these are all moderately reactivity metals. Okay.
Hmm.
Next. Here, we usually use electrometallurgy. Reason being, see, most of them will react, with water. So you cannot use it in aqueous solution. Is that clear? So that
Right.
means if at all I have some lithium metal, lithium in water will release electrons to become LiOH and H2.
Right.
Next. If you have manganese, zinc, chromium, iron, cadmium, cobalt, nickel, tin, H2, copper and mercury, then we use pyrometallurgy. For all these, we'll use pyrometallurgy. That means heating is more essential here. Okay.
Right.
These are relatively low reactivity. Then if you have silver, gold, and platinum, we use leaching. Leaching is done in aqueous solution. So that's why it is called hydrometallurgy. Okay.
Okay. Hmm.
Next, if you compare this one, when it comes to the concept of pyrometallurgy, and pyrometallurgy is easy for oxides because the reduction of sulfurs to sulfur is non-spontaneous. So non-spontaneous for reduction. The ore is generally converted into oxide in most cases. From any form, we will have to convert first into an oxide form. Okay.
Okay.
For example, if you have ZnS plus C, okay, ZnS plus C in the presence of O2.
Right.
So what do I get? The sulfur would convert into, one second. Yeah. If at all I directly use oxidation here, we can get ZnO plus SO2. Okay.
Hmm.
Or if at all I directly use with carbon and you are expecting this one, ZnO plus CS2. Okay. In the presence of O2. Clear?
Hmm.
Sorry. यहाँ पे ZnO नहीं. This is reduction. Z. Okay. Reduction. Z and CS2. But this
Right.
is delta G being positive. That means directly for sulfur to get sulfides to get reduced into those metals, that is less feasible. Hmm? But if you convert them into oxides first and then do the reaction, that is, I react ZnO plus carbon plus some O2. Now this time we will get Zn plus CO2. Are they clear, beta?
Hmm.
That's why in the procedure going ahead, everything which is converting into concentrate, we first convert them into oxide. Okay, clear? So we use
Yes, sir.
carbon and O2 or simply oxidation, but make sure that everything is converted into oxides.
Right. Okay.
So to
So,
convert, yeah, beta, to convert that into an oxide, concentrate to ban gaya hai. Now I need to convert that into an oxide. Then there are two methods we can do. One is called roasting, the other one is called calcination. Okay. Roasting is heating the ore in the presence of air, but the temperature at which you are heating should be below its melting point. Got it?
hmm.
Clear? So, for example, ZnS plus O2, that will become ZnO plus SO2. Okay? This is
Plus
roasting
O2.
because you're doing that in the presence of O2. Clear?
Yes, sir.
What are the benefits of it? first it becomes porous, you know, because the ZNO will have a lot of pores on it now.
Hmm.
So because of the pores being formed, surface area will increase. Hmm.
Okay.
And oxidation reduction reactions are taking place. It is
Right.
exothermic, energy is released. It is mainly
Okay.
used for sulfides. What are the volatile impurities which will come out? So if you have sulfur, it will come out as SO2, you know, in any other form they have, correct?
Okay.
So they all will convert into oxides, and whatever the metal or non-metal which is present in it, they all also will convert into volatile impurities like this.
Right.
Next, if it is about organic impurities, correct, they'll also decompose this way. Understood?
Okay.
Now, when it comes to calcination, calcination is also a heating, but it is in the
Yes, sir.
absence of air. Okay.
Okay.
So, for
Hmm.
example, if you have ZnCO3 on heating, it will become ZnO plus CO2. Now, what are the
Yes, sir.
benefits? Here, ore becomes porous,
Okay.
surface area will increase,
Right.
thermal decomposition is observed here. An endothermic reaction is the one which will happen here. And this is
Right.
used for hydroxides and oxo salts like
Oxalosalts.
carbonate or sulfate, or simple
Right.
hydroxides. All of them, they can be converted into respective oxides. And the impurities that we can remove out is basic metals in the form of on heating they can come out as vapors, or
Okay.
H2O, CO2, right? Because on heating, carbonate it will come out as CO2, sulfur will become SO3, like that. So we can get all of these volatile impurities out. Okay.
Hmm.
Now, roasting is also done in the presence of limited supply of oxygen when it is doing a partial roasting. Certain cases we do something called controlled roasting or partial roasting. Okay.
Right.
Now, control roasting or partial roasting would be very much essential, I mean, very much useful in case where a self reduction takes place. The important wording you are looking out for is self reduction. Okay.
Hmm.
Let me show you in which case it will happen. Okay. For example, if I take copper pyrites as the ore, and this copper pyrite ore is mainly used for extraction of copper. Hmm.
Hmm.
We have heated this in limited amount of oxygen. Okay.
Okay.
So you know that between iron and copper, copper will have more affinity with iron as compared to that of copper because of the charge it has. Iron would have +2, copper will have, +2 here. This has D10 completed already, isn't it?
Hmm.
So, but iron does not have the D10, so it will have more ability to form oxides. So, as you add limited supply of oxygen, iron will take away oxygen, convert into FeO.
Right.
Some part of sulfur will take oxygen, convert into SO2.
Right.
And the remaining part is copper and some more part of sulfur. So that will become Cu2s. Okay.
Hmm.
So actually CuFeS2 is a combination itself of Cu2s, Fes and Fes2. Okay.
Right.
And that on heating with limited oxygen now becomes FeO and Cu2s. Okay.
Right.
Now, even if some amount of Cu2s is converted into Cu2O, imagine if Cu2s is also reacting with O2 and converting into Cu2O, correct? So
Right.
then the Cu2O again reacts with the remaining amount of Fes, convert into FeO plus Cu2s. So in a way,
Right.
यही मिलेगा product, बराबर?
Right.
And once you get this FeO, I mean, once you make this reaction happen, then you will add some amount of silica to it, SiO2,
Okay.
and heat it. On heating it, whatever the amount of FeO present, that will react with SiO2, convert into a form called slag, a salt form which is called slag.
Okay.
Slag is basically a lighter, less dense, right? And
Right.
floats on the surface. It is a molten form and floats on the surface.
Right.
So this FeSiO3 will float on the surface, and in the bottom, what is remaining now? Cu2s. So Cu2s will be remain, correct?
Okay.
So
Yes, sir.
this remainder on the bottom here will have mainly 92% of Cu2s and 2% of FeS. That might be still unreacted part. Okay.
Right.
And this part is called as copper matte. So you got an idea what is
Okay.
copper matte, what is slag. Okay, go through it once.
Yeah, 1 second.
Check. Finished?
Right. 1 second. Yes, sir.
Right. Check out. Like I said, slag are immiscible compounds, less dense, float on the surface of the molten metal. Okay.
Right.
Now, when basic oxide impurities react with acidic oxide, or acidic oxide impurities react with basic oxides. What does that mean? Is there are acid-base reactions of two oxides happening. One is a basic oxide, the other one is an acidic oxide. For example,
Right.
FeO in this case is a basic oxide, SiO2 is an acidic oxide. When they both
Right.
combine, you will get something like a salt form, which is a slag.
Okay.
Now that can be reverse also. That is SiO2, which is an acidic oxide, can react with a basic oxide like CaO, and that can be used to remove CaSiO3. That is also a slag.
Hmm.
Okay. So flux are those materials that is used to remove the impurities. So in this case, these FeO is an impurity, SiO2 is an impurity. The material which you are adding to remove that, that is called flux.
Right.
For example, in this reaction, silica is acting like a flux. And there is some other reaction in which calcium oxide will be used as flux. Okay,
Right.
understood? Hmm.
Right.
Next. Flux are oxides used to remove the oxide impurities from slag. And slag is a very thermally stable compound. It can be made in the form of silicates or phosphates.
Okay.
Silicate slag is usually used in cement industries. Okay. And
Right.
phosphate slag is used in fertilizer industry. Like this is a very famous slag, calcium phosphate, known as Thomas slag. Ca3PO4 twice, calcium slag. Okay.
Right.
Hmm. Other slags are generally not possible. I mean, of course, there are some slags forming, but they are not very thermally stable. Okay.
Right.
Now, our entire discussion was about self reduction. That's what I told you. Remember this word, okay?
Hmm.
Correct? Self reduction is done when you are doing a partial roasting, correct?
Right.
How is that happening? See, at certain temperature, the oxygen affinity of sulfur is less than copper. Okay, this happens after a certain temperature, especially
Hmm.
with copper, lead, and mercury. Okay,
Right.
so sulfide ores of these three metals will be reduced partially by roasted ore, and this is called as self reduction.
Right.
How does this happen? Let me show you. We have PBS. You use limited amount of oxygen that is converting into PbO and SO2, correct?
Hmm.
But since you are adding limited amount, only some amount of PbO will be converted. I mean, some amount of PbS will be converted into PbO.
Right.
Now, this PbO and PbS together combines to form Pb plus SO2.
SO2.
ठीक है?
हम्म,
It is like this. ये
ठीक है.
2 moles हुआ, यहाँ पे 3 moles. This is the balance reaction. Hmm?
ठीक है. Yes. So
Same logic. If you take Cu2s plus O2, first it will convert into Cu2O plus SO2.
Cu2O, and then that will again react with
And
Cu2S.
now this Cu2O plus Cu2s will combine with each other to form 6 moles of C. This will form 6 moles of C and SO2.
Hmm.
Clear?
Right.
So this is how the reduction of copper will take place. Okay. So what are the three metals when you reduce by partial roasting beta? Lead, copper, mercury. याद हो जाएगा?
Hmm.
Hmm. A similar reaction will happen even with mercury also. Just like how we did it for lead, same reaction. Hmm.
Okay.
Now, so far, one thing we understood that except for these three metals which we are doing partial roasting, otherwise for most of the metals which may exist in carbonate, nitrate, sulfate, sulfide, in any form, first convert them into oxides.
Right.
Up to this point we came, correct?
Right.
Now once you get an oxide, from oxide you are supposed to reduce them to metal. Okay,
Right.
but to reduce them we require what? A reducing agent, correct? So choosing a
Right.
right reducing agent is the important deal. Okay,
Right.
so to do that, whether a particular reducing agent is correct or not, we need to theoretically understand using something called Ellingham diagram. Hmm,
Right.
correct? So here this will help us choosing the suitable temperature with a good reducing agent. Okay,
Right.
see this concept here. When metal is treated with O2, it will become metal oxide. This is
Hmm.
generally a spontaneous process. Delta H will be negative, a combustion type of reaction. You know? So delta H is
Right.
generally negative. Correct. But at the same time, have you noticed something? This is gas, this is solid, and this is solid again. What is happening to the entropy beta? Entropy is decreasing.
1 second. Uh, Solid and gas going solid. Yeah.
Yeah, entropy is decreasing, which means the feasibility of this reaction is also becoming temperature sensitive now. Although this is
Right.
negative, since this is negative, this part becomes positive, correct?
Right.
So since it is temperature sensitive now, if you start increasing the temperature, don't you think delta G will also increase? Which means the spontaneity decreases. Because for a spontaneous change, we expect delta G should be as negative as possible. But
Hmm.
in this case, if temperature is raised, delta G will also increase. Correct?
Right.
So you will often see, different types of slopes, right? As per that equation. Because this is like an equation of a straight line, right? Y is equal to mx plus c kind with respect to temperature, if at all I plot, isn't it? So let me
Right.
write down that y is equal to mx plus c. Here delta G is equal to minus delta S into T plus delta H. This is what we are talking about. Okay.
Hmm.
So if delta G is Y and temperature is X, then I need to analyze how delta S is, isn't it? See, this factor
Right.
is usually always a feasible factor. ये हमेशा negative होता ही है. Combustion is generally negative, correct? Generally. Not in all cases, I'll tell you that case also. Okay. Generally, it is
Okay.
negative. Okay.
Generally, it is negative. Okay.
Yeah. So it is delta S which becomes a very important factor here. Okay.
ठीक
So
है.
now notice, if delta S is positive by some means, then the slope is negative. So as temperature increases, delta G will decrease, right? That means it will only
Hmm.
become more spontaneous if you increase the temperature, correct?
Right.
So oxygen का affinity और बढ़ते जाएगा. That means metal will try to become more strongly associated, or any element will try to strongly associated with oxygen more as the temperature increases, correct?
Hmm.
Now, in that case, how does the slope go? I mean, how does the line go? This way, correct? Delta G versus T line will go this way. Best
Yeah. Hmm.
example, carbon. See, if I take carbon, 2 moles of carbon plus O2 will become 2 moles of CO. Now notice this
Right.
carefully. Reactant side, there is only 1 mole of gas. Product, we have 2 moles, which means delta S is positive. So if delta S is positive, delta H is negative. What should happen to delta G? That will become more negative as the temperature increases, isn't it?
Right.
That's why it is becoming more and more negative here. Clear? So
Okay.
carbon would start showing very strong affinity with oxygen as the temperature increases, and it exhibits more in the oxide, carbon monoxide form. Okay.
Okay.
Second case, if delta S is negative, slope is positive, and this is how it goes. And this is typically most of the metals, because for most of the metals, metal oxide is solid, and delta H is generally negative, and delta S is negative. So that is why as the temperature increases, it will go upwards.
Right.
That makes sense. Which means as you take them to the higher temperature, their affinity with the oxygen is decreasing.
Right.
Or I could say the other way around, that the backward reaction is more feasible as compared to forward reaction. Correct?
Right.
Okay. So if you have, when the above reaction is for solid liquid metal, so that means this is a solid or a liquid metal forming a solid, the graph would still be the same. Okay. Clear, beta?
Hmm. 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 Hmm.
But now notice, if the metal is gas, metal is liquid, or metal is solid, कैसे change होगा? If it is gas,
Right.
reactant side you have lot of gaseous particles, and here only solid particle, which means negative. The slope is very highly negative because delta S is highly negative. Correct?
Hmm.
Is that clear? So because delta S
Yes,
is
sir.
highly negative, that means in that case the slope would be like this. This will try to be more upwards, right? Like this.
Right.
And if the metal is liquid and delta S2 is negative, okay, in that case it will be like this. If it is solid, it will be like this. Correct? So for solid, it will be like this. Liquid, thoda sa slope will be slightly more in the negative scale, and this will be gas to solid, which will be even more. Okay. So you
Hmm.
can see delta S1 is greater than delta S2 greater than delta S3. Okay.
Right.
If I notice it for one particular metal, see, one metal, when it is solid and you are increasing the temperature as it becomes metal oxide, it will go
Hmm.
this way. From here, it has reached melting point. Let's say this is its melting point. So from here, it is liquid. So it will have a different curve like this. And after this point, when it reaches a boiling point, from there again it will raise up. Okay. And that's what you will
Right.
see. So there will be slight change in the curve like this. So where it is changing, there are 2 points where it changes. The point first where it changes will always be melting point. Second point where it changes will always be the boiling point. Okay.
Right.
So while analyzing the graph, you should be able to pinpoint which is melting and boiling point also. Okay.
Right.
Next. Now, notice for carbon dioxide. Carbon plus oxygen, it becomes carbon dioxide. This is 1 mole of
Hmm.
a gas. Product is also 1 mole of a gas. So delta is 0. Okay. And
Right.
this is a complete combustion. Complete combustion, delta H is negative, which means delta G will remain constant with a negative value.
Right.
That's why delta H is remaining constant with a negative value. So that means 0 line will be somewhere here. This will be negative value. Okay. This will be from
Right.
carbon to carbon dioxide. Clear?
Right.
So which means as the temperature increases, carbon's affinity to combine with oxygen will be very high, correct? And it will exhibit more into carbon dioxide. Okay. Yes, earlier I
Hmm.
said carbon monoxide also. That depends upon moles of oxygen. If you have less number of moles, it can become carbon monoxide. If it has more number of moles, it can become carbon dioxide. Okay.
Hmm.
Notice for carbon monoxide. For carbon monoxide, if you notice that I told you this, it will be going lower. Earlier I took that example. Okay. Now, if this is the case here, okay, 2CO plus O2 is becoming CO2. 2CO plus O2 is becoming CO2. Okay. Now, in this case, if you observe it, where is it? Yeah, one thing I forgot to mention here. Yeah, here I forgot to mention this has delta H being greater than 0. Carbon monoxide formation, carbon plus O2 forming carbon monoxide is uh, a endothermic process. Got it?
Hmm.
So delta G mainly depends upon the delta S value only. जितना ज्यादा पॉजिटिव रहेगा उतना नेगेटिव होना स्टार्ट हो जाएगा. Okay.
Right.
So which means when you have it at a very low temperature, let's say delta G is equal to delta H minus T delta S. So if you keep it at a low temperature, since this factor is anyway 0, sorry, this delta H value is anyway positive, correct? So this factor might be smaller than delta H. So delta G will be positive, no beta? So at low temperature, this might be, you know, more non-spontaneous. So high temperature only, this will be spontaneous. Okay,
Okay.
keep that in mind.
Right.
Next, if I take 2 moles of carbon monoxide plus O2, it will become 2 moles of CO2. This is delta H is negative. So it will have 2 mole and 1 mole converting into 2 moles, which means slope is still negative. So this is the way it will move.
Okay. Yeah.
Okay. If I club all these three graphs at a time, you can see C plus O becoming CO is this line. CO
Hmm.
plus O2 becoming CO2 is this line. C plus
See.
O2 becoming CO2 is this line. Correct.
Okay. Yeah.
Right. So
Yeah.
now from here we can say at the high temperature, which is more feasible, carbon monoxide is feasible.
Carbon monoxide.
Okay. At low temperature, which is more feasible, okay,
Carbon dioxide.
carbon carbon dioxide is more feasible here. Okay.
Hmm.
Clear. Now this is the Ellingham diagram of different metals. Okay. So let me analyze one by one. First, mercury and silver, both of them will have quite values above close to 0. This is delta G
Hmm.
being 0. Okay.
Right.
Now, which means if you notice their spontaneity is generally less to form oxides,
Yes,
because
sir.
they are approaching 0 very easily. Correct.
Hmm.
Which implies that if you are having an HGO around 400, around 500 degrees centigrade, let's say, do you think HGO will be stable beta? No, it will try to go back He plus O2. Done.
Okay.
So that means HgO does not have a strong affinity with oxygen at high temperature. Reverse is more feasible. That means HgO at high temperature will immediately reduce into Hg plus O2. Okay.
Hg plus O2.
So that is why mercury and silver, they do not require a reducing agent only. उनको सिर्फ हीट कर दो, अपने आप से वो मेटल में कन्वर्ट हो जाएंगे.
Okay.
You take their oxides, just put it at a slightly higher temperature, around 400 to 500 degrees centigrade. So they can
Hmm.
immediately convert into metals and oxygen gas will escape. This is how. Okay, clear? So this
Okay.
is a forward reaction, but backward is more feasible. Okay.
Okay.
Next, then you have copper, zinc, iron, aluminum, magnesium, all these metals, if you notice, obviously they are meeting the zero line at a very far distance, which means if you want them also to reduce into copper, it is very difficult. Correct? Just like how
Hmm.
happens for silver and gold. First, you have to experience a very, very high temperature. Okay.
Okay.
Getting that itself is difficult. And then you have to
Okay.
convert them into a solid metal form. Again, that is difficult. Okay.
Hmm.
So that's when we require a reducing agent for sure. Okay. Now
Okay.
let me show you this example with a zinc. Okay. For example, if it comes to zinc, zinc has, line this way. Okay.
Right.
Alexa stop. Okay. So zinc plus O2 becoming ZnO. This is the oxide formation for it. Okay. Now notice it
Right.
carefully. Zinc, and if you notice reaction at this particular temperature, see this is the temperature somewhere here close to
Right.
800. Okay. If I take the zinc oxide above 800 degrees with
Right.
some carbon in it, I add some carbon in it, then what is the expected reaction? Above 800
Should
degrees,
become
zinc
carbon.
plus O2 will become ZnO is not feasible, but C plus O2 become carbon monoxide is feasible. Correct?
Correct. Yeah.
So if I add these two, that means I can expect that ZnO plus C will give Zn plus Co. This is feasible because backward is feasible here, forward is feasible here, correct?
Correct. Yeah.
Which means this is that particular temperature above which zinc oxide will get reduced.
That particular
So
temperature
who is a
above
better
which
reducing agent in this case? Carbon. So we can take
carbon.
carbon for zinc. So to reduce the zinc, we can use carbon here.
Carbon. Okay.
Okay?
Yes, sir. So 1 second now.
Ah,
Information overload. Wait.
right.
So ठीक है. ठीक है. Okay.
Yeah.
Yes, sir.
Next. Same logic, if you take it for any other metals, you can do that. Okay. Now you might wonder, sir, zinc is here, correct? Aluminium is here, isn't it?
Right.
So why can't we use aluminium? Correct?
Oh yeah.
Because
Why can't we use
aluminium
aluminium?
will form oxide more easily. So in the presence of zinc, zinc can form zinc more easily here, isn't it? So yes, we can use aluminium also, correct? But
Okay.
better thing is you take something which will overlap. Okay. Of course. Yeah. Okay. So you
Yes,
can see
sir.
you can use this one, you can use this one, you can use even iron also to make the reaction feasible. Correct. So one thing
Yes, sir.
you notice that anything which is above will easily get reduced. Anything which is below will easily get oxidized.
Oxidized.
Okay. That is one thing
Yes,
you should
sir.
know. So in the case of magnesium and aluminum also, if you notice that, here you can see 4 by 3 aluminum, this one, this is supposed to get reduced more easily as compared to that of magnesium below this temperature. Understood? below this temperature. So as long as you're operating below this temperature, then yes, the reaction where magnesium getting oxide and aluminum oxide getting aluminum, that is feasible reaction. So that's why overall reaction, this is feasible. Yeah?
Right.
So that's how, based on the graph, you should be able to judge which one is a better reducing agent. Okay.
Right.
So you can see when it comes to copper, it is quite above, and carbon monoxide graph is meeting just here only. Hmm? So of
Okay.
course,
Yeah.
theoretically above this temperature, copper oxide is highly feasible to convert into copper, and carbon is highly feasible to convert into carbon monoxide. Okay,
Right.
clear with the idea, beta? Okay,
Yes. So.
right. So I would suggest you to quickly read these points and then we'll go ahead. Okay.
Okay.
Now let us understand what is refractory. Refractory or heat absorbents, okay, used to absorb heat in the furnace, during the extraction of metal. One thing you must have noticed from a Lingam diagram, that of course you are supposed to maintain high temperatures to extract metals. Hmm? So while that high temperature is happening, these are highly exothermic reactions, so heat is released. So we require certain containers which will absorb a high amount of heat. Okay,
Right.
that heat absorbents are called as refractory materials. Hmm?
Okay.
So high melting point compounds are used in the form of brick. For example, these combinations, they have very high lattice energy. They will be combined to form as a brick, and that will be used as a strong adsorbents. So first they
Right.
protect the inner and outer surface of the furnace from high temperature. Okay,
Okay.
clear?
Yes.
And
Sir.
inner temperature is important for us. Okay, high temperature is important.
Okay.
Clear? Next, reduction of ores. Okay, now the concentration was moved to reduction. Correct? Concentration is being now converted to reduction. Okay. Now, reduction methods, first term that is frequently used for reduction is called smelting. That is called smelting. Smelting means a slag formation with a carbon reduction. Got it?
Right.
So whenever we make a carbon reduction, preferably a slag is formed during that, right? Because you will add some flux also into it. So that
Huh.
process is called as smelting. Just like how we had roasting, concentration, calcination, there is this method for reduction of ores. We call it as smelting. Okay.
Right.
Now notice it when it comes to reduction of iron. Okay. Fe2O3 is present with silica as the impurity. Okay. The
Okay.
flux that is used is calcium carbonate. Okay.
Okay.
So the reducing agent we are using is carbon. And as per a Lingam diagram, we learned that there is a chance for iron to get it reduced. Where does it happen? It usually happens at 900 degrees. You can see iron's line is like this. Hmm? Correct.
Yes.
Iron's
Sir.
line is like this. And uh, where is it? Yeah. Carbon,
Hmm.
where is it? Here. Yeah. At this point here, this one. Okay. So you can see, no, here. This is iron form. Actually, the diagram got a little wrong. This is where it should be. This is where it touches. Okay. So as it touches here, that will be the carbon monoxide formation. Okay. So you can see
Yes. Sir.
carbon will convert into carbon monoxide and FeO will convert into Fe. Okay.
Hmm.
And there is some amount, if you notice, before this, this reaction is also feasible, right? Carbon monoxide plus O2 will convert into CO2, right? So
Right.
below 900 degrees, this reaction is more feasible.
Hmm.
Okay? Here also reduction is happening. And above 900, here also reduction is happening, but this time with carbon. So there are two
Hmm.
reducing agents here. One is carbon monoxide, one is carbon. So carbon monoxide is a reducing agent below 900 degrees. Carbon is a reducing agent above 900 degrees.
Right.
Done?
Right.
Right. So this is a typical flow chart. So when you have a combustion, so carbon dioxide formation, and carbon dioxide can form into carbon monoxide. Carbon monoxide will start moving up. Fe2O3 will keep moving down, and this is the reduction happens. Now, what exactly it meant?
Yes.
See, I'll show you in a blast furnace now. Then I'll relate that back. Okay. So this is the setup of blast furnace. How does it look like? Okay. So this is all the refractory material beta. Okay. We'll make a big hood out of it. And then here there are hot air providers. Here there is a hot air which will blast into it. And that is done by some kind of a fans. Those fans are called 2 airs. So these 2 airs will keep sending hot air. Okay. And here we add lot of coke. Clear? Carbon.
Yes, sir.
So carbon is added here first.
Okay.
And then from the top, right, we will add, sorry, there is a layer here in which have some coke already. And then
Okay.
from the top, we add the ore along with some limestone, right, calcium oxide, and then along with some coke. This is
There's
been
already
added.
coke down, you add more coke
Yeah,
from on
here
top.
a little bit of coke already there, and
Okay.
rest of the coke you add from the surface here. Okay.
Okay.
Now, as it passes down, correct. So there are three zones being created. One is a combustion zone. Next one is a fusion zone. The last one is a reduction zone. Okay.
Okay.
And whatever the gases after the reaction they are exiting, they all can be exhausted from here. Now,
Okay.
this is
Yeah.
what I'm saying. In combustion zone, what is happening? Okay. As it as the coke comes in touch with the oxygen, because hot air is being blown from here,
Hmm.
first it will convert into carbon dioxide. Okay.
Okay.
And as you start increasing temperature, carbon dioxide will start converting more into carbon monoxide,
Carbon monoxide. Hmm.
right? And this carbon monoxide which is forming will start keep moving up. Hmm? And if the temperature is appropriate, that means it is maintained around 900 degrees, then it will start reducing. That carbon monoxide, as it start moving up, it will start interacting with Fe2O3. And
Okay.
Fe2O3 step by step will start getting reduction. That is, Fe2O3 will convert into Fe3O4. That will convert into FeO, and finally that will convert into iron. In all this process, carbon monoxide is used as the uh, reducing agent, which will convert into carbon dioxide.
Okay.
Okay. In NCRT, these are the reactions given. So I would suggest you better remember them, how the sequence is. Okay. Between
Okay.
500 to 800, correct?
Hmm.
Between 500 to 800, directly FeO is not being used, but these oxides can get still reduced. Okay.
Hmm.
But only FeO will be above 900. Okay. Hmm.
Hmm.
So Fe2O3 is our main ore, right?
Hmm.
So that means it can interact with CO, it will convert into Fe3O4, that will convert into some part of iron. Fe2O3 will also convert into some part of FeO. Okay.
Hmm.
These reactions will happen between 500 to 800 kelvins. Okay.
Hmm.
Right. Next, 900 to 1500 K, you will see carbon converts into carbon dioxide. Okay.
Hmm.
And FeO, when it combines with carbon monoxide, will convert into Fe. This is the exact temperature. 1073 is the exact temperature where it happens.
Hmm.
And you are adding lime, right? That lime will react with the impurities present in the hematite, which is the ore,
Hmm.
Fe2O3 ore, and convert into a slag, calcium silicate slag. Okay?
Hmm.
So these are typical reactions happening in furnace. Hmm,
Hmm.
right. So this is the slag zone. Fe2O3 can be reduced before 900 degrees, and from there slag zone will come, and the slag zone will have calcium carbonate converting into calcium oxide, and that will react with silica to convert into CaSiO3, which is slag.
Right.
And rest of the form is iron, which got reduced, right? So that iron is the one
Hmm.
which is the molten form, which will be at the bottom. This is the molten form which will be existing in the bottom. Okay, correct.
Right.
So that iron form, which is at the bottom here, correct. So that can be removed out. That can be removed out of this. Clear?
Right.
And iron, which can be removed in the form of molten form here. And calcium silicate, which is present as the slag, will be always on the surface of it here. Now this will be in the liquid form on the surface of the uh, molten iron. So this one, in fact, this one is the slag, and this one is that molten iron. Okay.
Hmm.
So molten iron can be removed from here, slag can be removed from here. Okay. The bottom part where you will have the liquid forms is called hearth. Okay. Hearth can remove out this slag form. So this is a solid waste, which is a slag, and the iron which is just extracted iron is called pig iron. It is called pig iron. Okay.
Okay.
Now, if you notice how the working is, the blast furnace is charged by the raw material with the help of crane from the throat of the furnace. And in the combustion zone, first introduce the carbon from the throat and contacts with hot air balloon from down, and combustion of the carbon starts and carbon monoxide will form. As the temperature increases, carbon dioxide converts into carbon monoxide as well. And now carbon monoxide moves upwards due to gaseous state and start interacting with Fe2O3 with carbon monoxide, but reducing Fe2O3 first into FeO, and then it will reduce into iron. Its temperature is below the melting point, okay, and carbon converts into carbon dioxide. And calcium carbonate converts into calcium oxide, and it will react with silica to form slag. Fusion zone for solids now starts melting by moving down, increasing the temperature to 1503. This is where the iron will start melting, and that melted iron is called pig iron. So this is the overview of the uh,
Right.
things which are happening. Okay.
Hmm.
Clear. Uh, this is about extraction of iron. Okay.
Hmm.
We haven't discussed how to purify it. All purification will do it at the end. Okay.
Right.
If it comes to zinc, zinc has the ore ZnS, which is called as zinc blende or sphalerite. Okay.
Right.
The Ellington diagram, you can notice that zinc is here. This is how it is going, and it will get in contact at this particular temperature. This is around 700 degrees, I guess. Okay.
Hmm.
So ZnO will reduce above this temperature. Okay.
Right.
Clear, beta? So reduction of zinc takes place in a vertical retort. Okay. This is how the vertical retort would be. Okay. This is typically the setup. So iron, zinc oxide and copper, carbon will be added here. So now this is the refractory material which you will take it so that it can absorb the heat. So from here you will have an inlet to send the producer gas and air. Producer gas means N2, okay, CO and N2 plus uh, air, which is O2. You mix all of this and send it over. Clear?
Okay.
And as you add all of them and then you close it down, okay, because here there is a charging door which can be closed completely. So once you do that, now what will happen? See, ZNS will first get roasted. Hmm? First it will become
Hmm.
roasted, and ZNO is present here. That ZNO is reacting with the carbon which you added, and zinc will be coming in the form of vapors now, because the temperature at 700, it is already going to start vaporizing. Metal will start getting vaporizing. Okay.
Hmm.
Now you will take these vapors here, correct? These vapors will be collected through this side. So there is a chiller here. So that will instantly cool it. Okay.
Hmm.
So as you pass it through a rapid cooling, it will convert into an impure form of zinc. The zinc thus extracted is called spelter zinc, which is around 90% pure.
Hmm.
Done. This is about zinc reduction. Okay. So this is a typical working. You can just read it once and then we'll go ahead.
सर
हाँ
एक्सट्रीम ओवरलोड थोड़ा
हाँ बेटा,
पढ़ने दो
लास्ट
सर,
लास्ट.
1 मिनट. सर कैन यू गो अप टू द डायग्राम अगेन वंस?
Reduction of copper ore progresses through a Bessemer converter. Okay.
आई एम
So
सॉरी, व्हाट?
basically self reduction हो रहा है. Okay. बट
ओके.
सेल्फ रिडक्शन कहाँ पर होना चाहिए? एक ऐसा इंस्ट्रूमेंट,
बेसेमर
हाँ
कन्वर्टर.
एक ऐसा कन्वर्टर चाहिए जिसमें यू नो कॉपर मैट जो हमने प्रोड्यूस किया विच इज Cu2s, करेक्ट, दैट शुड गेट द चांस टू reduce into copper, right?
हम्म.
बेसिमर इन सिंपल टर्म्स अपनी रॉ टर्म में बोलो तो चाय की केटली. ओके.
ए यो. ओके.
बस उसी तरह का सेटअप. ओके.
ओके.
सो केटली लिया हमने, पकड़ा, राइट, और उसको ऐसे
हम्म.
झुला दिया. ओके.
हम्म.
और बिल्कुल वैसी होगा ये. सो इन ए
हम्म.
बेसिमर कन्वर्टर, controlled air is being passed with Cu2s and FeS. Okay. And we have seen these reactions before. So let me repeat it. FeS plus O2 will become FeO plus SO2. And whatever the FeO which is forming, right, we have added a flux which is silica. So these two will react to form slag. Hmm. And
हम्म.
Cu2s which is there as a copper mat, that will react with limited amount of oxygen to convert into Cu2O and SO2. Okay.
हम्म.
And this Cu2O will react with the rest of the Cu2s to get copper. Okay. Now the
हम्म.
copper which is forming usually will have a lot of small holes which we call it as blisters, because whatever the sulfur which was present, that is all coming out as SO2, so leaving little fluffy and blisters. Correct.
हम्म.
That's called blister copper. It is around 98% pure. Got it?
यस सर.
Done. Right. Next. Let's see Bessemer converter now. Okay. I mean, this is the way it will be. So यहाँ से hot air जाएगा बेटा. This is the molten form of copper which is formed, and above that we will have slag. Clear?
ओके.
Any doubt here? Okay.
नो
So
सर.
just read it once.
आई सी द केटल पार्ट ऑफ इट.
Hmm.
ऑल्सो सर पेस में अभी अपना
1 second. See, lead ore is galena. That when you
हम्म.
react with O2 will become PbO. This is also supposed to go for partial roasting and then partial reduction. So along with PbO, there is some amount of PbSO4 also forming, small amount. Okay. And both of them can easily get self reduction with rest of the PbS. So as you react with
हम्म.
rest of the PbS, you will get Pb and SO2 will be formed. Okay. So you can
हम्म.
see T2 is greater than T1 in this case. This is how the self reduction will take place. Clear?
राइट.
Clear? Any
यस
doubt?
सर. नो सर.
मर्क्यूरी सेम केस बेटा. मर्क्यूरी को दो तरीके से कर सकते हैं, लाइक आई टोल्ड यू. कंप्लीट रोस्टिंग करो तो भी मर्क्यूरी आ जाएगा, 400 डिग्रीज पे थर्मल डिकम्पोजिशन हो जाएगा. ओके. पार्शियल
राइट.
रोस्टिंग करो तो भी ये दोनों मिक्स होके वापस रिडक्शन हो जाएगा. दिस इज मर्क्यूरी.
राइट.
एंड टिन रिक्वायर्स कार्बन. सो देखो, सबसे पहले SnO2 in the presence of O2 will become SnO2 here, and copper sulfate FeSO4, ये दोनों CuSO4 and FeSO4 में कन्वर्ट हो जाएंगे. These are the impurities basically. Okay. And with water they are soluble form, तो ये separate हो जाएगा. SnO2 insoluble अलग हो जाएगा. This is a pure form which is called as black tin. Okay. And
हम्म.
instead of directly using a coke वाला carbon, we use anthracite coal. Okay.
ओके.
So anthracite coal will convert this carbon into carbon monoxide and tin. SnO2 into Sn, which is an impure form. Okay, this is around
Okay.
90% impure. Done. This is extraction of tin. Clear?
Hmm.
Last, chromium and manganese ka extraction is called as Goldschmidt aluminothermite process. Okay, so
Hmm.
wherein chromium will get reduced, chromium ore which is in the form of Cr2O3. Okay, that
Hmm.
when you react with aluminium, right? When you react that with
Right.
aluminium will get oxidized, chromium will get reduced. Okay,
Hmm.
aluminium when it becomes oxide, right, huge energy will be released, beta. Okay,
Right.
so that will help it to form chromium more easily. And but for that to happen, first we require initial energy burn करने के लिए, aluminium को burn करने के लिए initial energy चाहिए. For that
Okay.
we use some amount of barium superoxide or peroxide, which will give you O2, and that when you react with this is magnesium ribbon. Okay, so that will
Right.
release sufficient amount of energy so that aluminium can start reacting, molten form में आ जाएगा, and that will ignite these two reactions and convert that into chromium. Okay,
Hmm.
and same goes with manganese also, exactly similar form. Okay, you can read that once. How to do a thermite welding, railroad welding जो करते हैं, rails के बीच में जब भी gaps आते हैं, breakages आते हैं, how will they weld it? Okay, so they use a
Hmm.
thermite mixture which is Fe2O3 and aluminum with 1:3 mass ratio. Okay, and you just heat
Hmm.
it. Okay, here ये भट्टी होता है, like a, what do you say, uh, furnace. Okay, clear?
Okay.
So this furnace, a small furnace will be there in which aluminum will get oxidized, iron will get reduced, but huge amount of energy is released, because of which ये जितना भी iron metal होता है बाद में वो भी melt हो जाएगा.
Hmm.
तो उसके साथ में ये आयरन भी मिक्स हो जाएगा और सब मिलके जैसी कूल कर दोगे तो दैट आयरन लुक्स लाइक एज इफ इट वाज ओरिजिनल पार्ट ऑफ इट. ओके,
Right.
so that's how the thermite welding is been done. Okay.
Okay.
That's it. This is the part which you need to know. Next is a refining part. Okay, so that is the last
Right.
part of metallurgy which we'll discuss in the next class.
Hmm.
Got it?
Okay, sir.
Right.